We're going to use version 1 and version 2 because when I got looking at it, I saw that there were questions that were different for each one. It wasn't just the fact that uh, uh, there's different approaches to the same topics in one versus the other. They're actually unique questions for each one. So we're going to go through both of them. I've selected and highlighted the ones I want to touch on. And as always, if there's one in particular that's bugging you, just stop me and tell me we'll do that one before we do anything else. And if it happen to think of one in the middle of things, just tell me and we'll deal with it. Okay, version 1 first. I'm going to scroll down to question number 9. Right. Okay. Let's see. At 1 atmosphere, liquid water is heated above 100 degrees. So if we're talking about system, this will be our water, and its temperature is greater than 100 degrees, right? And 1 atmosphere pressure. So if it were in equilibrium with its surroundings, if it were in equilibrium with its surroundings, then the temperature would be exactly 100 degrees. But since it's greater than 100 degrees, that means we have to transfer energy from the surroundings to the system to get it higher than 100 degrees. That means the entropy of the surroundings should be negative. Let's see. Yes, less than 0. Okay. Otherwise, if we were in equilibrium, the surroundings would be equal to 0, and entropy here would be equal to 0. That's what happens for equilibrium. All right, number 10. Oh, that's B, less than 0. Say 10. Okay. At 1 atmosphere, liquid water is heated above. Oh. All right, we got the same situation. But now the question is, what is the entropy of the universe for this process? Well, the entropy in this case, we're actually talking about the whole universe. So every process increases the entropy of the universe. That's the second law of thermodynamics. Entropy for the universe is always greater than 0. When you're talking about the whole universe, we're not localized here. We're talking about everything. Okay. So A is the answer to 10 because it's always greater than 0. It doesn't matter what else we're doing. All right, let's see if I can get that. Here we go. Number 11. Which of the following is true? Okay, so we're going to have to look at each one of these. Let me get this out of my way if I can. Put it over here. All right, so E says none of the above is true. So essentially, we've got to go through every one and see which one is true. How about by spontaneous? This is A. By spontaneous, we mean that the reaction or process will always proceed to the right as written, even if very slowly, increasing the temperature. See. But so far, it's true. Right? That's what we mean by spontaneous. But there's more to this statement. Increasing the temperature may speed up the reaction, but it does not affect the spontaneity of the reaction. Changing the temperature will change the spontaneity. Yeah. So A in its entirety is false. How about B? It starts off the same way. Oh, except it says spontaneous to the left. No, as written, when we say spontaneous, we mean to the right. We'll go without any intervention. So B is false. C, by spontaneous, we mean the reaction process will always proceed to the left. There, that's false again. So we just stop there and cross C out. D, spontaneous means the reaction is always proceeds to the right. Yes, as written. Even if very slowly, increasing the temperature may speed up the reaction, and it generally affects the spontaneity of the reaction. Yes, it does. All right. So, because if we're talking about equilibrium, we know from experience that if it's exothermic, the heat term is on the right, and if you increase the temperature, you're going to drive it back to the left. That decreases its spontaneity. All right, so D is the answer. That's the one that's true. All factors taken into account. All right, let's scroll down. Well, let's see. How many am I taking from number one? Doesn't look like many, does it? Oh, there's 34. For the following reaction, carbon dioxide and water. Dioxide, water is in equilibrium with methane and oxygen. Yes. That's it. You're right. Okay, delta H is positive 803 under standard conditions equals positive 803 kilojoules. So we know that this reaction is endothermic. That reaction term, if we were to use it in, say, Le Chatelier's universe, we put it over here. Okay, now what's the question? Which of the following will increase K? All right, so we do want to put it over here. Right, delta H 0 over here. Now, when we increase the temperature, decrease the temperature, we're shifting the equilibrium, but we're doing it because we're changing the K. So if we increase the temperature here, we're shifting that way, which means we're increasing the numerator and decreasing the denominator, and the K will increase. If we increase the temperature, K increases. So if we increase the temperature, then K goes up because we're increasing the numerator, and vice versa. Okay, so let's see. Decrease the number of moles of methane. If we change the number of moles of any of these components, it doesn't change the K at all. Right? K is constant. The only thing that'll change the K is the temperature change. So C, increase the temperature of the system. Yep, that will increase K, just like I described there. So C is the answer to that one. Let's see, 36. Let's see, consider the gas phase reaction. So all of these are gases. NO plus a half O2. This is 36. NO plus half O2. Units in equilibrium with NO2. Yes. Yes. And the delta H is minus 56.9. Minus 96.1 And we're also given the K.
It's 56.
Excuse me. That wrong. Well, dyslexia is kicking in. And then we also know K. 1.46 to the 6 at 25 degrees C. So it's at the same temperature that this is. All right, what's the question? What would be the effect on the amount of NO present of compressing the equilibrium system to a smaller volume while keeping the temperature constant? If we compress the system, oh, this is the Chevalier. Yeah, what would be effect on the amount of NO if we compress the system? Right, we got 1 mole over here, right? Am I in the right chapter? And we got 1.5 moles over here. Right? So if we compress it, how's it going to respond? It's going to try to make fewer moles to relieve some of that stress. So it's going to shift to the right and decrease the concentration of NO. So B is the answer. Let's see here. 46. So aggravation, I'm trying to figure it out. Okay. So the following data are collected. Calculate the normal boiling point for formic acid. All right. So 46. What do we get? All right, if we're gonna do the boiling point, we have a situation where we're going from liquid to gas, right? So this is formic acid. That's one way to write formic acid. And it's going to gas. Okay. So we're also given the standard heat of formation for the liquid and the gas. Yeah, so we got L to H formation for the liquid is minus 410 kilojoules. And for the gas is minus 363. Right. We're also given in standard entropy. So it's minus 363. Oops, that should be joules. Entropies are usually given in joules. Yeah, is 363, 430. And 250. Okay, what's the normal boiling point? Right one. No, maybe the wrong version. It's 2. All right. All right, if we're working backwards, working backwards, we know that, and these formulas should be in the back. We'll be sure they're there. Yeah. Yeah, look at this one. Okay. Actually, we can start from this one. Delta S equals minus delta H over T. Excuse me. I get that backwards. Delta S over delta H. No, that's right. Only this is surroundings. At equilibrium, we can say that the system then is just change the sign. Okay. So what we need to know is what's the delta H and what's the delta S. In order to find the delta H and the delta S, all we need to know is what are these values, and we know how to calculate each one. So the delta H for that reaction is just minus 363 minus a minus 410. Okay, so 363 subtracted from 410 is what? That's 47. This is 47 kilojoules. And then the delta S for this system is 251.1 minus 130. Let's see. And that's 121.1 joules. Now, the way this is set up, this is going to be in joules, that one has to be in joules. And the way I do it, I just say, convert that kilo to 10 to the third. So 47 times 10 to the third would be the value you put in here. We have to use the same units, right? Same size units. So if we solve for T, that's T equals delta H over delta S. And delta H is 47 times 10 to the third, and delta S is 121.1. So let's see, let me flip that around, multiply that times 1,000. Right? Flip it and divide. So we get 388 K. But the units of measure are degree C. So how do we get K out of that? I mean, degree C? Minus 273, right? That should be 115. Degrees C, which is E. So we worked everything from this relationship here. Relationship between delta H and delta S for the system. And this change in the sign only works at equilibrium.
Wait, so where do we get the 270?
Oh, it's from first semester. K equals C plus 273. So C is K minus 273. See what you missed?
Yeah. Let me try and get this to my calculation. All
right. So I'm gonna go down and keep scrolling, see if I can find another one. There's another one. 52.
So all you did was just shifted, because I'm getting 3.88, so we just shifted that over to 388.
When you get 388, you subtract the 273 to get the 115.
Yeah, what I'm saying is I'm getting 3.88, so we just.
Ah, well, do you have 4.7 times 10 to the fourth divided by 121?
I got to the third.
Well, 47 times 10 to the third, yeah,
Yeah,
divided by 121.
yeah, and I'm
Isn't
getting
that 388
3.88,
times
10 to the 7.
10 to the double?
Okay, so just shift there to 2.
Right, and then subtract 273 from it.
Okay.
It'll give you 115. Okay, all right. Next. All right, 52. Let's see, calculate delta G zero for water plus oxygen yields hydrogen peroxide at 600 K. All right, so we're given the different Ks for reactions that we're going to use to create the target reaction. This is the target reaction. Let's see, water, gas, they're all gases. Plus 1/2 O2 is in equilibrium with hydrogen peroxide. Okay. And this is, we're at 600.1 K. Are you allergic to this class? Let's see. Well, it could be that fan stirring up all the dust too. All right, so we have K values. Those Ks are in partial pressures. Okay. We need this equation from those two equations. So the first equation has hydrogen peroxide on the correct side. Okay. So we can include that one. Let's see, hydrogen plus oxygen. Yields hydrogen peroxide. And K for this one is 2.3 times 10 to the 6. 3. And 6. All right. So we got this one taken care of here and here. We've got actually too many oxygens here, but we want to keep it like that. So we're going to get rid of half of those oxygens, I think, in the next step. The next one has water on the right-hand side, the second equation, and we need it on the left-hand side. So what we have to do is flip the equation. And we've got 2 waters there, and we only need 1. So we have to flip the equation and divide it by 2. So we've got, well, here's the flipped equation. And then 2H2 plus O2. Okay, and we need to cut this one in half. All right, so the original KP was 1.82 and 37. And 7. So what do we do with the K when we flip the equation? Take the inverse, don't we? Right? Because you put the reactants where the products are and the products where the reactants are. So the expression itself inverts. So we need the inversion of this one. Plus, what do you do when you multiply by a constant factor? That becomes the power. Right, so we take the inverse of this one, take 1 over 1.8 times 10 to the 37. And then we take the 1/2 power, which is the square root. Okay, that's our new K. KP for this one now is whatever that turns out to be. 1.8, 37, going to invert it. And then I'm going to take the square root of it. So, I don't want to steal your thunder. Has anybody got that yet?
Times 10 to the negative 19.
Yeah, let's round it off to 2.4 times 10 to the minus 19. So this is the one for the modified equation. This is the one for that original. Now, do we end up with this one up here? Okay. So this one becomes 1. This one becomes 1. This one becomes 1/2. So 1/2 on this side and a whole on this side gives us 1/2. So we put those together and we get this one. We've got 1 hydrogen on this side and 1 on this side. That's out. We got 1 water on this side and 1 water on that side. So we're good. So now we have we can calculate the K for this reaction. And what would that be? It would be this first K times the second K. So we've got 2.3 times 10 to the 6th times 2.4 times 10 to the minus 19. Right?
5.5 times 10 to the 30. Negative 30.
Right. We can keep 2 significant figures. 5.5 times 10 to the minus 13. So now we have the K for that reaction. Let's go back to the question. Calculate delta G. We know the K. And we want delta G. And this is K. Well, yeah, K is at equilibrium. So that goes without saying. And delta G0 uses that K in this equation. Okay. So, which one of the R's is it? It's the one with joules in it, right? 8.3145, is it? I think. And the temperature is given 600.1 K. And then we take the natural log of 5.5 times 10 to the minus 32. Okay. Let's see what that gives us. Let's see.
Is that a negative?
Uh-huh. Yep. Sure is. Oh. Messed up. I'll do it again. There.
It's negative 2.4 times 10 to the negative 9. So we're getting.
Oh, I messed up some. I had to start over again. I'm almost there. So I get,
Yeah, you got that.
I'm still messing up. Hold on a second. 5.5 exponent -13. Take the natural log of that.
Oh, I'm not taking the wall. That's what I'm doing.
Take the natural log of that.
Now, what is that again?
Natural log of this. Don't you have an alien key in there
I
somewhere?
do.
Okay,
So
yeah,
it's -10.
-28.2289. Then times 600.1. And then times 8.3145. And then times the negative. So let's see, let me move. Why is it giving me standard notation? I want scientific. Display. Scientific. There. Okay, two significant figures there. 1.4 10 to the 5th joules, but our answers are given in kilojoules. So if we take 10 to the 3rd out of that 10 to the 5th, right? Remove 10 to the 3rd out of that 10 to the 5th, would leave us with 10 to the 2nd. So 10 to the 2nd is 100 times 1.4. 1.1 140. Actually, if we want to, this would be 1 that would be 1 kilojoules, and it's positive. That comes closer to the answer. So that's the free energy. Positive free energy means what? It's not spontaneous that way. Negative delta G is spontaneous. Under these conditions. All right. That took a little longer than expected. All right, number 53. Consider the reaction 2NO2 yields N2O4. Yes, and we're also given delta H0 is minus 56.8. Kilojoule. This is exothermic. And delta S0 is minus 175 joules per K. What else do we get? In a container, 298. 298 is 25 degrees C. So that's under standard conditions. The initial pressures are 2.4 for N2O4. 4 atmospheres. And 0.042. No, 0.42 atmospheres. Initially. Which of the following statements is correct? Which way will the system go? All right, in order to say which way it moves, we need to calculate the Q and compare it to the K. Right? That's the way we tell which way it goes. So we need to We need delta G. Oh, I was looking at the wrong one. All right. Or the other thing we can do is we have two options. Delta G zero. Delta G zero is the equation we were using earlier. Minus RT log K. Okay. And then another one is delta G zero equals delta H zero minus T delta S zero. So in order to find out the K, we need delta G. And we have delta H, and we have delta S, and we have the temperature, so we can calculate this delta G. So if you want to, you can do this one first, then use this one to find out what K is. Or you can combine the two equations, and I think that's the way I did it in word problems. And solve for K. Then all you have to do is punch in the values and you get K in one calculation. So we have the common term here is delta G. All right, so if A is equal to B and A is equal to C, then B is equal to C. So we just say, all right, so this is also equal to delta H minus T delta S. And then we solve for K. Right? So let's put everything on this side except for the K. That gives us, let's take the negative with us. So log K equals delta H 0 minus T delta S 0 divided by minus RT. Okay. I think that's what. Yeah. I don't see any way to simplify this one very easily. So we have the delta H 0, and these all have to be in joules. So now we have to convert this one to joules, like minus 56.8 times 10 to the third joules. So that's delta H. Minus 56.8 times 10 to the third joules. And then minus this term, which is 298 K times delta S 0, which is minus 175. Okay, and then we're divided by negative 8.3145 for the R value. And then the temperature is still 298. Okay, so that should give us the natural log of K, and then we can solve for K after that.
You have negative 5.68. Like when we worked it out,
Minus 56.8 kilojoules.
yeah, you have.
Oh,
negative five.
Minus, wait, which one is wrong?
So you have there negative 56.8, but then your work, like the worked out paper that you gave us, you have negative 5.68. So 10 to the 4.
That's the same. Yeah, it's the same number.
Okay.
Yeah, you just take a power of 10 by moving this one here and put it over there. Yeah.
You got me all worked up over here.
I'll leave it that way because my calculator doesn't care. Okay, so let's see. I can put this one in 56.8 exponent 3. Change the sign. No, this side. Now change the sign. There we go. And then 298. Here is 175 change the sign times, and then subtract that from the other. So I get minus 4.65 times 10 to the third here. And then divided by 8.3145, I'm just going to ahead and make that one negative and divide that into it. And then divide 298. So I get 1.877 here. And then K is the anti-log of that value, which would be what? E to the 1.877, right? As the base is E, so E to this power is that value. So I just need to go in here and find the E to that power. There we go. So K is equal to 6.532. I'm gonna keep some decimal places. So go back to a question. Which of the following statements is correct? Okay, so now we know the K. We can calculate the Q and compare it. So the Q is going to be the actual concentration of N2O4. And then in the denominator, NO2 squared. So in the numerator, we're going to have 2.4 atmospheres and 0.42 squared. That's our Q. 0.4 and then 0.42 squared by the. So I get 13.6. The Q is larger than the K. That means we've got too much on this side. Right? So it's going to move to the left. And then to answer the question, the first one says some of the N24 will decompose into NO2. That's good. I like that answer. Yeah. So we had to do all that mess just to calculate these two values and compare them.
So I'm not getting 1.877, I'm getting like 1.66.
Okay. Let me check this. I get.
I mean, it's definitely something that I'm doing. So no.
Okay. So if your number is smaller than this one, that means this one is either too big or this one's too small. More likely this one's too small.
Let me put in here first, because I was putting it directly what was off this sheet, so they try to.
Okay. Aren't those the numbers I have on there? Yeah, the same numbers in the word problems. Anybody else try it? No luck.
And I'm getting a negative 4.65, getting that.
Up here?
Yeah, I'm getting that number correct.
Okay.
And I divide it by,
You got a negative 4.65 up here.
yeah. To the third. Or 10.
Times 10 to the third. Okay. Then just divide it by a negative 8.3145.
And then multiply that by the.
No, and then divide by 298. That's the problem. See, this is still in the denominator, so you have to divide whatever you get by that number. You get something up here, divide by that, divide by this.
Okay, so you're dividing it separately. Because I'm putting it all together in one, like one.
Oh, you can
equation.
you can calculate this one and divide it into that one.
Yeah, I'm still getting 1.66.
What do you get? Nothing?
Negative 5.6.
All right, you're getting, let's see if I get the same number here as you get. 56.8 x 3. I want to change that sign. And then 298 times 175. And subtract that. So I get -465. Okay, I got that same number. Let me see what I get on the denominator. 8.3145 times 298. So this one is -2.48 times 10 to the third.
They get the negative 4.6.
Okay. You get this one on the denominator? Negative, you didn't get that number? 8.3145 times 298.
Oh, wait, yeah, I think that's what I would do.
3.48.
Right, for the denominator. Then just divide that in this.
Yeah.
And I get 1.877.
One point eight five four eight.
Really?
Yeah.
$1.875. Okay.
Yeah. Now I'm getting the 1.75.
Okay. If you punch these numbers in after you've done these calculations, that you get 1.875. If you let your calculator hold the number with infinite decimal places, then you'll get 1.877. But you should get the same answer when you compare this one to that. This one, right? If we use that one as our power of E, let's see what we get. 6.52. So if we had a 5 here, we have a 2 there, right? And you still get the same answer. So which way does it move? If this is bigger than that one, then it has to move to the left.
So how do I take the cake on?
I-
The 1.877, what the hell? How do I do that on my calculator?
When you do this calculation,
Yeah.
you have to leave it in your calculator.
Yeah. I'm picking
You
up
good?
and putting down now.
Okay. That was 53. Okay, let's see, we got any more? 56. Consider the following system at equilibrium 25 degrees. PCl-free gas plus chlorine gas. PCl plus gas yields. I'll bet $1, it's PCl5 gas. And delta H 0 equals negative 92.5 kilojoules at 25 degrees. Well, that 0 means standard conditions, so it's 25 degrees. If the temperature of the system is raised, the ratio of the partial pressure of PCl5 to the partial pressure of PCl3 will what? I think this should be fairly simple, right? If this is an exothermic reaction, then we put the delta H on this side. And if we increase the temperature, you increase the temperature, which way is it going to shift? We're adding this component to it that way. So the ratio of partial pressure of PCl5 to the partial pressure of PCl3. Okay, that means this one decreases and that one increases. So the ratio is going to go down, it'll decrease. This ratio will decrease. And we didn't have to do any calculations. That's nice. All right. Anybody else? Vote 58. Okay, I got a note to go to version 2, number 56 after this one. It's probably based upon the same information. So let's do 58 here. The equilibrium constant for the dissociation reaction Cl2 to 2Cl was measured. Cl2 to 2Cl. Yeah, the equilibrium constant is measured. So what is the constant? It should be Cl squared over Cl2. As a function of temperature in K. So we've got a set of data where we measured the Kp versus the temperature in K. Right. We got a bunch of data here. Okay, a graph of Kp versus 1 over T, log Kp. So we're going to transform this to a log Kp versus 1 over T. And that's what we're going to plot. All right. So if you go to useful information, you'll find that I think this is the Uranus plot. Where is it? Okay. Log K versus minus E sub A over R. So if we plot it, log K minus E sub A, activation energy over R times 1 over T, and then plus delta S over R. Okay. See if I got all my terms there. Oh, delta H0. So my mistake. This is not. There we go. So that's the equation that describes this plot. That means that the x-axis is 1 over T. There's y equals mx plus b. And this is going to be log K. And you're going to have a negative slope here. And where it intersects there is your delta S over R. That's the y-intercept. And the slope equals minus delta H over R. Okay. All right. The slope is given as minus 1.651. Minus 1.651 times 10 to the 4th. Now what's the question? Oh, the intercept is 14.51. So this one is 14.51. There we go. That's everything that's given to us. Now what's the question? Which of the following statements is true? The reaction is exothermic, endothermic. The reaction rate is high. The reaction is not spontaneous. We can determine exothermic versus endothermic. All we need to do is say, okay, if this is delta H over R is a positive number. So if delta H is positive and we multiply by a negative, we get this negative number. Right? So this has to be positive in order to give us that negative, right? That means it's endothermic. Okay, so B is your answer. Now, can we tell whether the reaction rate is high? No. This is only an equilibrium situation. Right, because we're temperature against K, that's equilibrium. So we can't say anything about the kinetics. The reaction is not spontaneous. We could say something about that, maybe, if we were able to calculate an individual K against the, and calculate the delta G. But that's a whole lot more trouble than we need, because it doesn't say two of the above or B and D. So I would pick, the best answer is endothermic. We can determine that this is an endothermic reaction from that information. Okay. Right. Now, let me see. Wants me to go to 56 version 2. So let's see. I can scroll down in mine because I got them both back to back. 56 version 2. That's just so I don't have to write it on the board twice. Should be the same parameters.
Let's say,
Different question. The value of delta H for this dissociation. Okay, so we're gonna, this is version 2, number 56. Is the one we're gonna do now. So we know that delta H over R equals this number, and we know what R is. So if this is negative and that's negative, we can just throw those out. Right? They cancel each other. And then R is 8.3145. And this is 1.65 times 10 to the 4th joules. Okay. So let's see what we get. See, our answer is in kilojoules, so we're going to have to convert afterwards. 8.3145 and 1.65 times 10 to the 4th. I get 1.372 times 10 to the 5th joules. And if we extract a 10 to the 3rd out of that, we get 10 squared kilojoules. Right? So in standard notation then, this is 100 times that value, which is 137 kilojoules. And that would be, B's the best answer.
So going back to the last problem, like what you said, so it can't be negative, it will have to be positive.
Yes,
Okay.
Yeah.
So that helps us limit.
yeah, they're both
Okay.
they're negative. This is negative from the formula, and this is negative from the slope. And the only way that you can have yeah, the only way you can have negative here and negative here is if this is positive.
So we had to make the 8.3 positive because of that. Correct?
Yeah, I just threw the negatives out. I mean, we could keep the negatives on the inside and then get rid of them later.
Yeah.
But I got rid of them first.
Okay.
Okay, so that answers 56 version 2. So let's see, where were we? 58. Let me go back up and see if there's any more after 58. There's 58, 59, okay. So we're going back to version 1 again. And this is 59. Okay, for a certain process at 300 K temperature, delta G is minus 10.4 kilojoules. Delta H is minus 7 kilojoules. If the process is carried out reversibly, the amount of useful work that can be performed is. The amount of useful work that can be performed is 10.4 kilojoules. Well, negative 10.4. Right. No big mystery there, right? Because delta G is Gibbs free energy. We call it free energy because that's the energy available to do work. Right? That's the amount of energy that can do the maximum amount of work. That's why it says in a reversible process. Only in a reversible process can you get the maximum amount of work out of that energy. And as a practical matter, that never happens. This is the upper limit. You learn about limits and capitals. All right. Now we're into version 2. Make room for a 2. And we go to number 2. All right. Oh, probability. A 2-bulb flask contains 5 particles. What's the probability of finding all 5 particles on the left-hand side? All right. Let's see. 5 particles. So we have all 5 particles over here. All right. What's the probability of finding 1 particle on one side versus the other 4? That's 1/2, isn't it? How about finding 2 particles on the other side? Okay. And finding 3 particles. And finding 4 particles. And finding 5 particles. So it should be 2 to the 5th power. 1 over 2 to the 5th power should give us the fractional value. So that's let's see, inverse. This is 32. So we take the inverse of that here. And this is 0.00315. No. Wrong place. Yeah, that's right. So this is the fractional equivalent times 100 would be the percent equivalent. 3.13%. So C is your answer. And now we're going down to number 14. For the process, CHCl3, trichloromethane, CHCl3, gas, I assume. Oh, that's a solid, sorry. We're melting trichloroethane. This is going to be cold. HCl3 liquid. And the delta H for that is 9.19 kilojoules per mole. 9.19 kilojoules per mole. And delta S is 43.1. Delta S is 43. Joules per mole K. Okay, what's the melting point of chloroform? Number. Right. Oh, we did one like this before. Right, where delta S for the system is equal to delta H over T, right? Yep. So we just have to solve T because this is an equilibrium. And we know what delta S for the surroundings is equal to minus delta H over T. So we just change the sign as long as we're in equilibrium. So T equals delta H over delta S. So, and this has to be converted to joules. 9.19 back. 19 times 10 to the third joules. And then 43.9 per. Okay. All right. I get 209.3. This is K, so we subtract 273 from it. And I get degree C is minus 63.736. So I was right, it's cold. It's very cold. Minus 64 degrees C would be the best answer out of those choices. All right. Who's next? Number 20. Put a marker. In which case must a reaction be spontaneous at all temperatures? Right. This is where we use the Gibbs free energy. Delta G equals delta H minus T delta S. So under what conditions would it be spontaneous? Under all conditions? This has to be negative, right? So how do we get negative out of this one? Always negative means that's minus and this is plus. Because that negative makes this minus. And your answer is always minus. So let's see. D. Delta H is negative, delta S is positive. That will always give you a spontaneous process. Okay. All right. Moving on. Let's see here. How about 26? Do I need to keep that up there? Probably. When a stable diatomic molecule spontaneously forms from its atoms, what are the signs? Delta H, delta S, and delta G. All right. A diatomic molecule spontaneously forms from its atoms. So a diatomic molecule, let's say X here, spontaneously forms from its atoms. And this always takes place in gaseous state. Remember why? Because you don't want phase changes to interfere with your measurements. So everything happens in the gas phase. Right. So if it's spontaneous, what does that say about delta G?
Negative.
Oh, yeah. Negative. Okay. We can say something about the delta S in terms of randomness. If you're going from 2 here to 1 there, that's a negative delta S. Right? So this is negative. Okay, now we just have to say delta H. All right, what happens when two separate atoms come together and form a bond? They give up energy, right? There are higher energy states like this. When they come together, they give up energy as they form the bond. We know that because in order to get those things apart, we have to pump energy into it, break the bond. So it gives up energy. That means it's exothermic. They're all negative. So that's E. Now, let's see. Under what temperature regime would this remain negative? It says it's spontaneous, but we can change it. These are standard conditions. We can change it from spontaneous to non-spontaneous. All we have to do is make this one more positive than that negative. So a high temperature, negative high temperature would make that one positive. More positive than negative. So at high temperature, this reaction, at some high temperature, this reaction would become non-spontaneous. So we want to keep a low temperature for this one to work. Uh, 31. Calculate KSP. What? Oh, okay. I thought we were in the wrong chapter. No, that's okay. KSP for sodium chloride. So sodium chloride, solid, goes into aqueous solution as this ion and this ion. And we want to know the KSP for that. Well, we know that the KSP is just going to be sodium times chlorine. But we don't have those values, right? We do have the delta G values, delta G formation for each one of these. So with that knowledge, if we know the delta G of formation for each one of these, then we can calculate the delta G as the sum of the delta G's for these two. So the delta G of sodium ions is, and there's 1 mole of each one. So we don't have to, we're multiplying everything by 1. It would be minus 262. Minus 262. And then chlorine is, chloride ion is minus 131. Okay. Yep. And then we subtract the sodium chloride solid, minus 383.8. Hey, now, what are the values here? These are in kilojoules. Kilojoules. Delta G and would be 2, 7, 1. Okay, so I get for this or here, I get minus 393. This is a negative times a negative, that's a positive. So I'm going to add 383.8 to that value. And this is minus 9.2 kilojoules. Okay, that gives us the delta G. And the relationship between K and delta G under standard conditions is delta G equals minus RT log K. Okay. So log K would be delta G divided by minus RT. And delta G is, and R has within it joules. not kilojoules. So this has to be converted to joules. So it's minus 9.2 times 10 to the third joules. This is minus 8.3145 joules per mole K. And the temperature is the standard 298 K. There we go. So it's a negative divided by negative. We can just ignore that. Okay, and I'm going to divide by 8.3145 and then divide by 298. And I guess log K equals 3.713. And then K would be e to that value. Right there. So I get 40 points. Actually, 41.0. Rounded off. Or 41. Best answer is A. So far, so good. Okay. It's 31. And let's see, next highlighted one is 34. Consider the gas phase reaction. NO plus 1/2 O2 yields NO2. We looked at that one before. For this system at equilibrium, how will raising the temperature affect the amount of NO present? Oh, okay. All right, so if we've got NO gas plus 1/2 O2 gas in equilibrium with NO2 gas, correct? And the delta H is minus 56.91. Where does it go? This side, right? Plus delta H. Okay. So if we raise the temperature, we're going to drive the reaction back this way. Correct? So the amount of this is the same one as before, isn't it?
And the other one, and then decrease.
Oh, the parameters are different. Raising the temperature increases NO. A. Yeah. Okay. All right. Number 40. This looks like a definition. Second law of thermodynamics states delta S for the universe is always greater than 0. So B is your answer there. All right. 43. Oh, did I miss one? Well, 42. Yeah. I'm having trouble today.
Sure.
Yeah, it must be the heat. A mixture of hydrogen and chlorine remains unreacted until it's exposed to ultraviolet light. So a mixture of hydrogen, gas, and chlorine gas doesn't react it needs an activation energy. It just sits there and does nothing until we add the energy to it. And this gives us 2HCl. Yes. Okay. Ultraviolet light from burning magnesium strip. Then the following reaction rapidly occurs. Which of the following is consistent with this information? Well, the delta G is a negative 4554. Delta G is negative 4554 kilojoules. Delta H is negative 44.12 kilojoules. And we probably got a delta S there also. 76 joules per K. Okay. So which of the following is consistent with this information? The reactants are thermodynamically more stable than the products. Yes. If you draw the diagram, this is negative. So that means we have to start up here and go down here. So the products are more stable than the reactants. Okay. So A is true. A is true. How about B? I have it false. Thermodynamically more stable than the products. Oh, yeah. I read it backwards. The reactants are not more stable. The products are more stable. False. The reaction has a small equilibrium constant. Well, the equilibrium constant can be calculated from the delta G. Equals minus RT log K. Okay. So if this is minus 45.54 times 10 to the third equals a minus 8.3145, and standard condition is 298 K and log K. Then I will take this one and divide by these two. Well, it's still a negative. There we go. And then 290. Then I'll take that to the E power. So I get a K of 9.6 times 10 to the 7. Right? So B is false. It's not a small equilibrium constant, it's a very large equilibrium constant. How about C? Ultraviolet light raises the temperature of the system and makes the reaction more favorable. No, it doesn't. It provides energy, but it has no effect on the temperature. So C is false. All right. How about D? The negative value of delta S slows down the reaction. No, this is equilibrium. Thermodynamics is an equilibrium situation. It says nothing about kinetics. Well, that was false. Process of elimination, A should be true, E should be true. The reaction is spontaneous. Yes, spontaneous. But the reactants are kinetically stable. We can say that they're stable, kinetically stable, because we have to put energy into them to make it go. Otherwise, they just sit there and do nothing. So E is the true one. We had to go around the barn several times to get that one. I think I'm picking up the dust now. All right, 43 down to 52. Let's see. Equilibrium constant of a certain reaction was measured at various temperatures to give the plot shown below. What's the delta S for the reaction in joules per mole K? All right, we go back to the equation. And I'm gonna cheat so I don't mess it up. Log K minus delta H log K equals minus delta H0 over R. Yeah, times 1 over T plus delta S 0. That right? Yes. Okay. So the question is about delta S. So we need to look for the value that y-intercept on that graph. So what's the y-intercept? Y-intercept equals 3.0, doesn't it? 3.0. So that means delta S 0, and I'm going to go ahead and divide it by 8.3145 equals 3.0. So 8.3145 times 3 is delta S. Let's see, did it round? Yeah, round it off. Two significant figures. Delta S equals 25 joules per K. Okay. Right. Excuse me.
Wait, I'm thinking excited about that.
Oh, I just multiplied this times that.
I divided, that was right. I see what you do.
Okay. Let's see, we did 56 already, didn't we? Is that the one we came down from version 1? Okay, so we can skip 56. Yeah, we did that one already. 57. All right, for a certain process at 300 K, delta G is minus 12.2 and delta H is minus 7 kilojoules. If the process is carried out so that no useful work is performed, delta G is what? The value of delta G tells you the maximum amount of work that you can get out of it. If you don't get any useful work out of it, does that change delta G? No. Delta G is still the same. You just didn't get any work. You just wasted all that energy. Right? So you converted all that energy into waste heat, essentially. So the delta G is still 12.2 kilojoules. E. That was a trick question.